Water. We're going to look at a brief chemical summary of water, looking at some of the properties and what we'll be needing to describe how water is important for biology. So first off, the density of water. Here it is graphed here. Notice the y-axis doesn't have a huge variance in the amount here. We're looking at pretty precise numbers here. But if you were to graph the density of water over a change in temperature, what we can see is that it is most dense at 4 degrees. So this is pretty unique. Most substances, as they cool down, they will become more dense. As they heat up, they become less dense. But with water, there's this curve. It's not a linear relationship here. We actually have this peak at 4 degrees, meaning water is more dense at 4 degrees than it is either below or above 4 degrees. So if you have, which is important for a lot of biological systems that live in cold areas, is that when water is at 0 degrees, it turns to a solid, it freezes, and the density of that solid, it's going to be quite a bit less than the density of the water itself. And if the density of ice is less than that of water, ice is going to float. And you can also see this is the reason why if you're going swimming in a lake or something like that, if you're down at the bottom, there's going to be colder water than there is up at the top, even if it's not sunny out for that, the sun heating the water itself. But actually the cooler water that is around 4 degrees will sink to the bottom, and warmer water will definitely be on top. But that cooler water tends to be at the bottom. However, when it freezes, that ice, which is less dense, is going to be at the very top. Ice floats. So, ice is a solid, less dense than its liquid form. The reason why it does this is because of the shape of water. We have these polar molecules, and so we're going to be looking at this sort of space-filling model where you have the oxygen and you have these two hydrogens bonded to it, and it ends up forming this particular shape to it. It's a polar molecule. You've got the dipoles with the oxygen and hydrogen bonds, and then you have hydrogen bonding between the molecules. So the intermolecular force is a hydrogen bond between one water molecule and the other. And what this is going to do is it's going to orient them in a particular way. And so you end up with all of these spacing. When they get locked into their ice solid configuration, they end up taking up more space than when they are able to move around freely. So if they get stuck into one single spot, they get frozen, they have to be oriented in a particular way, and that ends up with them being further apart than when they're able to freely move about in their liquid form. So again, this is a reason why ice is less dense than liquid water. Another really interesting property with water is its cohesion and adhesion. As we mentioned earlier, it's a polar molecule. It's quite a polar molecule. For its size, it sticks together really, really well. And this, when we have one water molecule sticking to another water molecule or a bunch of other water molecules, the term we use for that is cohesion. They're sticking to other water molecules. But water will also stick to other substances that have polarity as well. So if you have a substance, let's say like a cotton t-shirt, the water will stick to it fairly well because cotton also has some polarity to it. So any other substances that are polar will also attract water, interact well with water, and we call that adhesion. When you have other substances sticking to water, being attracted to water, that's called adhesion. And plants use this because plants don't have a heart. They've got to pump liquid throughout their structure from the bottom to the top in most cases, almost all cases, and they have no pump mechanism, so they're relying on this adhesion. You can see this with tubes as well. If you have here on the left is a thick tube, water can stick to the sides, but there's going to be a lot of water in the middle that doesn't have access to the sides of the tube. And so if you set up a thinner tube and a thinner tube and a thinner tube, so as we go to the right here, the tubes are getting thinner. And what you can see is that, let's get a different color here. What you can see is that the water in the tube rises further and further and further up the tube as the tube gets more and more narrow, because there's more side area, think of it like surface area connection to the sides of the tube, more ability for the water to stick to the tube. There's more adhesion, and therefore the water molecule is essentially able to climb up the tube. Now a plant, its xylem are basically a whole bunch of really small tubes, and therefore the water is able to move its way all the way up in this case it's a piece of celery, but could be like a giant sequoia tree, and that adhesion allows that water to move because it's attracted to the substances, the cellulose that make up that xylem. We can see cohesion in this picture here. So if you have something that is not very attracted to water, like hydrophobic, like the wax of a leaf, or let's say the wax of a car, if it's especially waxed, water will sort of ball up on it because it doesn't really want to interact with the non-polar wax surface. And so all the water molecules end up sticking to themselves nicely, and you end up with these little droplets. This cohesion also allows for surface tension of water as well. The water molecules at the surface, they're going to grab onto all the water molecules around them, which are really kind of only beside them and below them. They grab on them quite tightly, and so you end up with a certain amount of force that is required to break through that surface. Those water molecules, if you want to separate them, you gotta give them some force. And so if you don't put too much force on them, you actually don't end up breaking through them. So things like insects are able to step on water as long as they spread their weight out. And as long as it's not too much weight over not too much of an area, over enough of an area, they will be able to actually step on the water without breaking through. And it's not that they're floating, it's that they are actually stepping on the water molecules, and the force of those water molecules, the cohesion specifically at the surface, which we call surface tension, is actually holding that spider up, or if you were to jump into that amount of water, you'd actually feel the force required to break through those hydrogen bonds between the water molecules. Heat capacity is another really important thing for biological systems. In water particularly, it has a very high heat capacity. So these little water molecules are quite polar, and therefore they like sticking together, right? This is why they coheed to each other, if that's a word, but they stick together quite well. They have these hydrogen bonds that hold them together. Again, it's between molecules, so that's an intermolecular force, and it's a pretty strong force. So if you want to start moving them around, which is what you're doing when you're heating things, is that you're taking a little particle and you're making it vibrate faster than it was before, that you're heating it up. And so if you want to do that, you've got to move it. But if it's really attracted to all the things around it, that's going to be harder to do. If it's not that attracted, it's easier to do. And so since water is really attracted, one water molecule is really attracted to another water molecule, if you want to start moving them around, you can do it, but it's going to take a fair amount of heat. So it has a high heat capacity, and therefore it takes a lot of energy to heat up water. Solubility, another really, really important thing. You've probably heard water referred to as a universal solvent. It dissolves lots and lots of things. And it does this because as long as the thing that it's trying to dissolve has a charge, and that could be that it's polar or that it's ionic, chances are water will be able to interact fairly well with it. Doesn't mean necessarily it'll dissolve super easily, but if it is polar, if it's ionic, water will have a easy time interacting with it, because you have the dipoles in water, you have this polarity or full ionic charges in this thing that you're trying to dissolve, and so it'll probably dissolve into water. So here's a picture again of our water molecules. Remember, they don't have full charges. Those are partial charges here, so we should actually put like a little lowercase delta positive and lowercase delta negative for all these guys. But the fact is, it's polar. It's quite polar. And so if you have ions, the positive part of the water is going to be attracted to the negative ions, and therefore you'll probably be able to separate those ions and get them surrounded by the positive charges of a bunch of different water molecules. And then the opposite would happen with the positive ions. They would be attracted to the negative part of water, and therefore ionic substances tend to dissolve quite well in water. Hydrophilic is the term that we use for compounds that interact well with water. So hydro referring to water, philic referring to it likes it. So compounds that interact well with water, and again, you know the chemistry behind this. This is because the reason why they do this is because they have charges, either dipole charges for polar molecules or full-on ionic charges for ionic substances. Hydrophobic would be the opposite. And now this name's a little bit deceiving because you think it'd be like repelled by the water. It's not really, right? So all molecules are going to have some Van der Waals forces or London forces, dispersion forces, whatever you want to call them. Molecules are attracted to other molecules all the time. So what's happening with hydrophobic substances, compounds that do not, and again, this isn't really true, they still do interact with water, but the thing is water would rather interact with itself. So you'll see that oil and water don't mix. And so if you put oil drops into water, they won't mix very well with the water. And that's because oil is nonpolar. It doesn't have these charges that polar molecules do, or ionic substances do. So the oil sort of gets excluded by the water. The water would rather hang out with other water molecules and sort of kicks the oil out of the solution almost, or doesn't invite it into the solution anyway. It's not being repelled by it. It's not a repulsive force. It's just that water is so attracted to other water molecules, it leaves out the oil. So in biology, this is a really important concept because a lot of times we want to separate aqueous environments from non-aqueous or have other substances that aren't dissolved into that aqueous environment. And so this sort of interaction between what can dissolve in water and what can't dissolve in water is quite important. Last concept, quick mention of acids, bases, and these things called buffers. So aqueous solutions, if you have an acid, it has to be in water. This is why we're talking about when we're talking about water. So aqueous solutions, if they have these hydronium ions, or if we're being lazy, we can just say hydrogen ions, which really get attached to a water molecule and become H3O+. So these hydronium ions, they're in aqueous solutions. They're also hydroxide ions in these solutions as well. Something that is an acid will release hydrogen ions, and that's how we get these hydronium ions. If you take a hydrogen ion and you add in a water molecule, you get a hydronium ion. That's a 3. And so that's what happens when an acid interacts with water. It produces these hydronium ions. Bases essentially will increase the hydroxide ion concentration. A couple of ways of doing that. So they can just release them directly, or they can make water release them. But anyways, they increase the amount of hydroxide ions. So if you have more hydronium ions, there's more hydronium ions than hydroxides, it's an acid, and it'll end up having a pH below 7. If you have fewer hydronium ions, so then you have lots of these hydroxide ions, it's going to be a base, and it ends up with a pH above 7. Remember, pH, when it's above 7, it's a base. When it's below 7, it's an acid. If the hydronium ions and hydroxide ions, and remember a lot of times we just say hydrogen because we're being lazy, so hydronium or hydrogen is equal to the amount of hydroxide ions. These square brackets refer to the concentration of them, so the amount of them within a given volume. So if those two concentrations are equal, the solution will end up being neutral. If you mix an acid and a base, so something that has too many hydrogen ions and something that has too many hydroxide ions, you put them together, they can actually neutralize each other, and they will come together and form water. So these hydrogen ions, if you add them to hydroxide ions, you've got two hydrogen and oxygen and a plus and a negative charge, you can put them together and you get a water molecule. So that's a neutralization reaction. Buffers essentially lessen the effect that acids and bases have on a solution. So if you have a solution that has a buffer in it, what it does is if you were to try to make it more acidic or try to make it more basic, it would sort of resist that change. And this is really important in biology because if you change the pH, if you make it more acidic or more basic, the molecules that are in there end up getting changed as well, which is bad if you're trying to use those molecules to stay alive. So buffers can actually stop that change in pH. And they do this by accepting or releasing hydrogen ions.